Okay, so I'm going to go over the introduction to vector notes and just be aware that as I go through this, that you can look down into the speaker notes, and there is an introductory video here that is great on vectors and scalars. Okay, so first off, we're going to start off talking about forces. So a force is any push or pull in a simplistic definition, and it is a vector quantity. So when we look at this airplane here, we see that there are four forces that are acting on the plane. And the length of these arrows, these vectors, are indicative of the magnitude of the force, the strength of the force. So the longer the arrow, the stronger the force, and also the direction. So because it's a vector, it has magnitude and direction. And so the magnitude is indicated by the length of the arrow, and the direction is whichever way the arrow is pointing. So then we're going to talk about free body diagrams, and there are some conventions in setting up free body diagrams. So here we have a situation where a car is at rest. And so there are two forces that are acting on the car at this moment. And so first off, we want to make sure that we draw something that looks something like a car. So we have our car. And then we want to identify where the center of mass is. And we're going to assume the center of mass is here in the center of the car. And then we're going to draw our forces that are acting on the car. So one, we know there is a downward force. The car is being pulled down by gravity. The force of gravity acts on the mass, and so that gives us the weight. So we're going to draw a downward arrow, and we're going to label it mg, mass times gravity, which is going to be the force of its weight. And then because the car is in what we call static equilibrium, it's not moving, therefore there has to be another force that's offsetting this downward force, and it's got to be equal and opposite to this one. And so there is an upward force that is provided by the ground, which is pushing the car up, and it pushes the car up with the exact same magnitude of force. So you'll notice that the downward arrow and the upward arrow are the same length. That's very important because it shows us that when I add these two forces together, I come up with zero. And that means that this car is in static equilibrium, which means it is not moving. The sum of the forces acting on it are equal to zero. So now we have a different situation. Now this car is driving at constant velocity. And that's an important term right there, constant velocity. It means that it is not changing its motion. In other words, it is traveling at the same velocity. That means the same speed and in the same direction. And that also means, because I'm saying constant velocity, I know that the sum of the forces acting on this car are going to cancel out once again, and they're going to equal zero. So just like before, we still have, it's got weight, and that's the downward force. The ground is pushing up on it with the same force of the downward force. So the normal force, that upward force, is equal to its weight. But now we've got the engine is pushing the car forward, right? So it is driving down the road. But as it's going down the road, there's friction between the air and the tires that are going to cause a resistive force. And in the situation we have here, the force provided by the engine is equal and opposite to the force provided by friction. Okay, so the sum of the forces are all going to cancel out to give you zero. And this car is in what we call dynamic equilibrium, meaning constant velocity, zero acceleration. Okay. There's another situation that we could have where, so once again, the downward force of the car's weight and the upward force of the normal force are balanced out, so it's not moving up or down. But then we have this situation where the resistive forces are not exactly balanced with the force of the engine. So this car is not going to be in equilibrium. We call it non-equilibrium, and it's actually going to be accelerating. So when the sum of the forces are not equal to zero, you get acceleration. So if the net force is not equal to zero, you have acceleration or a change in velocity. So this car is accelerating this way. Now here's a really important thing to get. That does not mean that this car is moving to the right. This car could be backing up. The guy was backing up, and then he steps on the brake and he is going to accelerate forward, which means he's going to decelerate in the backward direction. And that is really confusing, but it will make sense as we go along, okay? So just know that the car is accelerating in this direction, but it does not necessarily mean the car is moving in this direction. And we'll revisit that again another time. Okay. So then we're going to talk about equilibrium. Okay. So if the upward force is 50 newtons and the downward force is 50 newtons, if the force to the right is 30 and the force to the left is 30, it's an equilibrium. All the forces are going to cancel out. And because they cancel out, the net force is zero. Now, it could be in static equilibrium or dynamic equilibrium. I don't know. This box right here could be moving upward at a constant velocity, in which case it would be in dynamic equilibrium. It could just be sitting here, in which case it's in static equilibrium. But in either case, if it's in equilibrium, as this one is, all the forces that are acting on it cancel out and they equal zero. So the sum of the forces, sigma F, equals zero. So the sum of the forces are zero. There is no net force. Same situation here, 50 up, 50 down, they cancel out. 75 right, 75 left, they cancel out. Sum of the forces equals zero, okay? So again, this is a situation where you see the difference between static equilibrium and dynamic equilibrium. So in this case, static equilibrium, it's not moving. The golf ball is sitting on the tee, and the normal force provided by the tee is equal to the weight of the golf ball going down, it's mg, and it is just sitting there. In this situation, say you drop a feather and you see the feather fall, it doesn't accelerate down for the most part. It's going to fall at a constant rate. And because it's falling at a constant rate, that tells you that the air resistance up is exactly balancing the weight of the feather down. It's going to continue to fall down, but the forces cancel one another out, and the feather doesn't accelerate. It just falls at a constant velocity, and that's called dynamic equilibrium. In the case of non-equilibrium, you step on the gas pedal, your car accelerates forward. That's why it's called the accelerator. If you step on that pedal, you are going to go faster and faster. Your speed is going to increase, and you are in non-equilibrium because you're accelerating. You can also accelerate by slamming on the brakes, and your car will decelerate, right? You'll slow down. Your acceleration will be in the opposite direction, okay? So here we're going to get into adding up your forces. So here we have two vectors in the same direction. And so vector addition tells us if they're in the same direction, you add them together. So say this is a force of 5 newtons and this is a force of 5 newtons, you're going to end up with a force of 10 newtons because they're in the same direction. If they're in opposite directions, you subtract. So a 5 Newton force to the right plus a 5 Newton force to the left. In this case, it's labeled -5 because it's in the opposite direction. And because force is a vector quantity, it has direction. So 5 plus -5 gives you 0, okay? Again, 5 and 10, 15, they're in the same direction. So over here, we have this car that is going to the right. And if I were to say, what do you know about this car? You would say, well, I know that if it has a 10 Newton force to the right and a 7 Newton force to the left, there is a 3 Newton net force to the right. That means this car is accelerating to the right, okay? So then vector is a quantity that can be described by magnitude and direction, such as force. And again, we use arrows to describe their magnitude and direction. The longer the line is, the greater the magnitude, the stronger the force, if you will. And then we also need to be careful about the angle of that force. Okay. And so in this instance right here, if you measure this angle right here to be 52 degrees, these angles get kind of strange on how to kind of label them. So this 52 degrees, if you just wrote the magnitude of the force was, say, in this case, 32 meters per second, and it was at 52 degrees, well, 52 degrees from where? So you need to make sure you're saying where that's coming from. So if I look at this line here, north, and I measured this angle here, so I'm measuring it from north, then I'm going to say that 52 degrees is east of north. So north would be straight up, and then I measured it east of that. So what's the magnitude of the force east of north? And that's where that 52 degrees comes from. Okay, so then we're going to look at scalars. And scalars are things that are described by magnitude only, meaning just the amount of. And so you're given some examples here: volume, time, area, speed would be another example of scalars that just have magnitude, just how much. So if I talked about, how much space did that thing occupy? Well, it was 20 milliliters of water. Well, 20 milliliters doesn't have a direction. If something was traveling at a speed of 5 meters per second, in that case, we say speed, which is a scalar. But if I said it was 5 meters per second to the north, then I would say it's velocity. Velocity is a vector and speed is a scalar. So if it has direction, it's a vector. And if it doesn't, it's a scalar. Okay. So then we're going to get on over here to vector addition. And we touched upon this a little bit earlier, but we're going to talk about this tail to head method. And so if I have one vector and another vector, and they're in the same direction here, I just lay the tail of one to the head of the other, and I add them up. And you can see that the length of this arrow is equal to the length of this one plus this one. And so this result of these two is called the resultant. Okay, so a lot of times you hear me talking about the resultant force, the result of two different forces or more, and then the resultant is what comes from those. Okay, and so there is a mathematical way of doing this, and then there is a visual, graphical way of doing this. And so we're going to look at the graphical way a little bit more here. And so if I have these two vectors, A and B, the result of those two vectors you can see right here. And so it looks like I skipped a page here. Or no. So coming back from here, I'm sorry. You have this vector A and this vector B. Well, if I put the tail of this vector to the head of this vector, you see that I get this resultant. And you see that they line up, and I jumped ahead a little here. I'm sorry. But you can see that that the resultant here, starting from where A did, it ends up right here where B ends up. And so we'll look at that a little bit more in depth here. So we have this pirate problem, right? So the muscular pirate R and the other pirate, Big Belly Burl, are both trying to pull or push on this treasure chest. Now, R is stronger and so exerts a greater force, a larger magnitude in one direction, and then Big Belly Burl pushes it or pulls it in another direction, and we're going to see what the result of those two forces are. Okay, and so we can see it over here that the result, is going to be visualized in this way. There it is. So in this case, I'm doing what's called the parallelogram method. And so I took the two forces that were acting on the chest, and then I made a parallelogram from them. And so I made a line parallel to this one here, and a line parallel to this one here. So I've got my parallelogram, and then my resultant comes from the vertex of the two and goes across diagonally, and this is the resultant force of these two forces that are exerted on the chest. So it doesn't go the direction of B or the direction of A. It goes somewhere in between them. And you can see it's more towards the A because that A is a greater magnitude force. So it's going to have a greater influence, if you will. Okay. And the length of this line, you can see, is not the same as either of these. This is the resultant force, and it's taking into account both A and B. Now, the head to tail method is a little bit simpler, and that involves just taking A, the force exerted by R, and then putting the B, the Big Belly Burl force, from head to tail, and then the resultant force is found right here. And you can see that the resultant force here is identical to the resultant force here. It's just using a different method. Okay. The other cool thing is if I were to take Big Belly Burl's force line and put it here, and then put args attached to it, the result would be in the exact same spot. So it doesn't matter which one you put first, you are going to end in the exact same spot. Okay. So then right over here, if you are rusty on trigonometry, your SOHCAHTOA. SOHCAHTOA is going to be a pretty important aspect of calculating the angle of these forces and determining the magnitude of them. So here's a quick Khan Academy video that you can watch that will kind of walk you through if you just need a little extra help, but that's not necessary if you don't need it. So if you're feeling good about SOHCAHTOA, we are going to see how we can apply it to solve some physics problems. So we have Charlie here that is pulling this sled with a force of 25 pounds and at an angle of 42 degrees from the horizontal, okay? So his force of 25 pounds, that is not the X and Y. So we want to know what the X and Y components of this force are. Okay, so we are going to resolve those forces. And so we need to look at SOHCAHTOA. And so Mr. Gray has been kind enough to set this up for us. And so that 25-pound force is acting at a 42-degree angle from the horizontal. What is the X and what is the Y? And so we have a right triangle here. And so if we want to know the Y, you can see that the Y is opposite of that angle. And this here is our hypotenuse. So if we know this angle, we know the hypotenuse. Well, we're going to use sine in order to find out what this Y component is, this vertical component of the force. And so here you can see you have Y equals 25, which is the hypotenuse, times the sine of 42, which is this angle, and you come up with 16.7 pounds. Now, if we want to know the X right here, this is the adjacent of this angle. And again, we know the hypotenuse, so we're going to use cosine in order to solve that. And so X equals 25, the hypotenuse, times the cosine of 42, and you come up with 18.6 pounds. So here's another one where we have a model airplane that has 45 newtons of thrust directly north, so upward, we're going to say north is up, and a wind is providing a 30 Newton force towards due west. Okay, what is the net force on the plane? So remember that a force is a vector quantity, which means it has direction and magnitude. So we need to get both of those. Okay, so once again, Mr. Gray has been kind enough to set this up. So due north, there's that 45 Newton thrust. And then to the west, there was a 30 Newton wind. And so setting this up head to tail, and then you've got your resultant here. But once again, we have a 90-degree angle because that intersection of north and west is going to give us our 90-degree angle. So once again, we can use our SOHCAHTOA and Pythagorean theorem. So if we know this and we know this, so we call this A and this B, well, this is C. So we're going to do our A squared plus B squared equals C squared, and we're going to plug in 45 and 30. And if you solve that out, you're going to come up with 54 newtons for the hypotenuse. So that's the magnitude. So anytime you see what is the magnitude, we're looking for that number. So a 54 Newton force. But in what direction? Well, so now if we know this and this, we know, and this is our angle right here, right? So it was going west of north, okay? And our angle here is going to be come from our adjacent and our opposite. Since this is our hypotenuse, if we know the adjacent, we know the opposite, we're going to use our tangent function. And because we're trying to find this angle, we're going to take the inverse tangent. So we take the inverse tangent of the opposite over the hypotenuse, and you're going to come up with 30 over 45, and that's going to give you 37 degrees. Okay, make sure you're not in radians on your calculator. If you do this and you don't come up with 37 degrees, you're probably in radians, and you need to switch that. Okay. Then once we have this 37 degrees, we have to once again remember that you can't just say 37 degrees, because 37 degrees from what? Well, 37 degrees to the west of north. Okay, so be careful with that. Kind of look at, you started going north, it went to the west. So this angle here is 37 degrees to the west of north. Okay, these are a little bit simpler, kind of just, again, adding vectors. And so here we have an upward, let's just assume that this is a force, a 4 Newton force up and a 4 Newton force down. They cancel one another out and you get 0. This is an equilibrium. Here we have, we're going to assume this is a right angle. We have a 4 Newton force up, a 3 Newton force to the right. And we know that if we remember our 3, 4, 5 triangles, that this would have a magnitude of 5 newtons, and the resultant would be in this direction here. Okay. Here you can see that this 2 and this 5 should cancel each other out, so that you're going to end up with a 3 Newton force downward, a 4 Newton force to the left. And so once again, you're going to have a 3, 4, 5 triangle here. And then over here, we have a 7 Newton force up, 3 to the left and 10 to the right. This 3 will cancel out with this, so you're going to have 7 and 7. And then you'll be able to calculate this force here to be 10, about 10, okay, 10 newtons. So just as you look at this, remember that, so if you have 3 forces here, you need to kind of figure out which ones cancel each other out, get it down to your 1x and your 1y, and then solve for your resultant force. So Mr. Gray has worked all those out for you right here. And then just last kind of thing, again, you have your x component of a force, you have your y component of a force, and then the resultant of those two is called the resultant. The hypotenuse of your x and your y is your resultant, okay? So here are some practice problems that I would like you to get done for the next class, and which would be on Wednesday. And submit these through Google Classroom. Feel free to talk to anyone you would like on this, like try to get some help, work together, but do your own work, please. Okay, and then make sure you upload this to Google Classroom. And then last but not least, make sure that you fill out your attendance form and try to get that done before 3 o'clock. And hope you have a great day.